Friends, in this lecture 41, we will discuss more on explosion modeling and steps towards fire protection as advised by international codes and other general safety practices which are commonly followed in offshore industry. We already said that levy is one of the important source of explosion. There are different sources. Of levy. Let us see them as listed below. 1. It could be a result of corrosion of walls of a pressure vessel. It could also arise because of mechanical damage caused to the vessel by impact loads. Can also be due to the absence of pressure relief valves. It can also arise, as we said in the last lecture, overheating. Can also be due to vapor, space explosion. The primary reason for occurrence of levy could be exposure to higher temperature. And exposure to more ignition sources. You can look at these 2 points. Very interestingly, these two are inevitably present in offshore platforms, being process or production or even storage platforms. These two could be very highly present because of the complexities involved in oil and gas production process itself. Let us look at a typical value. A typical value of liquid contained in a vessel. For our understanding, we need to look at this example value. Let us take liquefied natural gas LNG. Generally, the tanks or the tankers are designed to store LNG at a pressure of 250 psi, which is the working pressure. So, here we are talking about pressure vessels which deal with highly flammable liquids at a very high pressure. Let us look at levy modeling. E is given by P1 minus P0 by nu minus 1 the whole multiplied by V, where P1 is the initial pressure, P0 is the standard pressure, usually it is 14.7 psi atmospheric. E is the explosion energy, V is the volume of the vessel, and nu is actually the heat capacity ratio. of the expanding gas. In case of a compressed vapor, it is given by the following equation, which is an empirical equation where W is the energy in LV in terms of TNT equivalence, V is the volume of the compressed gas in cubic feet, P1 as we said is initial pressure of the compressed gas, which is in PSI atmospheric. PO is the standard pressure, which is actually approximately equal to 14.7 PSI atmospheric. P2 is the final pressure of the expanding gas, which is again measured PSI atmospheric. T0 is the standard temperature, which is 492 degrees R, where Rg is the gas constant, which is 1.987 Bt units per Lb mole degree R. This 1.39 10 power minus 6 is actually a constant which takes care of the units to get W in energy terms, which is actually a conversion factor. The units of this conversion factor is in Lb mole pounds TNT divided by feet cube Bt. Further, Pb is given by Ps 1 minus 3.5 nu minus 1 Ps minus 1 by root of gamma T by m 1 plus 5.9 Ps raised to the power minus 2 nu by nu minus 1, where Pb is called the bursting pressure, which can be in bar absolute. Ps is called the pressure at the surface. Of the vessel, is again in bar absolute. Nu is heat capacity ratio of the expanding gas, which is actually equal to Cp by Cv, and T is absolute temperature of the expanding gas in Kelvin, and m is the molecular weight of the expanding gas in mass per mole. The next consequence of fire in oil and gas industry could be fireball. Friends, if ignition source is present, which is very much true in an oil and gas production platforms, and the vessel is in contact with it, with the ignition source, then the consequence is more catastrophic. It will result in formation of a fireball. Fireball can result in two outcomes. One, it can cause thermal radiation. Two, it can also result in direct flame contact. Maximum diameter of the fireball is given by D max, which is equal to 5.8 1 by 3 where D is the maximum diameter of the fireball in meters and m is the initial mass of the flammable liquid in kg. So, that is the first parameter we are interested in. The second parameter about fireball is that the fireball combustion duration. T Blavy will be 0.45 m 1/3 can also be equal to 2.6 m 1/6 for m less than 30,000 kg for m greater than 30,000 kg. Call equation number 5. The next parameter could be center height of the fireball. Again in meters, height of the fireball is given by 0.75 of the maximum diameter of the fireball. The fourth parameter could be initial ground level hemisphere of the fireball, because fireball will form in a hemispherical manner. So, that initial diameter is given by 1.3 times of D max. Radiative flux of the fireball which is another important issue to estimate risk assessment, arise from fireballs. This is the one which is received by the black body. So, that is given by ER is wave E F21, where ER is emissive radiative flux received by the black body, which could be in the units of energy per area time. Tau A is atmospheric transmittivity, which is given by 2.02 Pw into S raised to the power minus 0.09, where Pw is the partial water pressure, XS is the path length, which is essentially the distance from the flame surface to the target. F21 is called the view factor, that is effect of radiative flux on the black body, let us say that is 2, caused by emission of the fireball, which is 1. So, that is F21. E is radiative flux emitted from the surface, which is given by R m H c by pi d max square T W, where E is radiative flux, R is radiative fraction of heat of combustion, usually taken as 0.3 for fireballs from vessels bursting below the relief set pressure. It is taken as 0.4 for fireballs from vessels bursting above the relief set pressure. M is the initial mass of the fuel, in the fireball, H c is the net heat of combustion per unit mass, D max is the maximum diameter of the fireball, which we already gave the expression, and T Blevi is duration of the fireball, for which also we have the expression. The next consequence which is interesting is flash fire. Flash fire is a non-explosive combustion of vapor cloud resulting from the release of flammable material in open air. Let us ask a question: what are the major hazard consequences of flash fire? The major hazard consequences are 2. 1. Thermal radiation, 2. Direct contact with flame. The energy release is given by this equation ER, which is tau A E F21, similar to that of the earlier model, where ER is emissive radiative flux received by the black body measured in terms of energy per area time. Tau A is atmospheric transmissivity, it has no units. E is the radiative flux emitted from the surface. F21, as explained earlier, is called view factor. Friends, having said this, let us talk about different methods of fire protection. There are different methods by which fire protection can be ensured. Offshore platforms are generally designed to be self-reliant even in the case of fire. There are reasons for this. The reasons are: there will be no fire rescue facility available in the near vicinity area. Of offshore platforms. The second good reason could be fire accidents cause many significant consequences. So, we need to avoid them completely. Fire protection can be achieved by using flame arresters. These are actually passive devices that are designed to prevent propagation of gas flames through pipelines. The second method what people generally follow is construction of fire resistance barriers. Third could be fire insulation. Fourth method could be by designing a proper water shower. Fifth could be by controlling fire using foams, and next could be by controlling fire with water spray. To understand fire protection, let us try to understand now what are the source from which the fire can be originated. You know, inflammable gases are inherently present in offshore platforms. Therefore, preventing sparks is the highest priority. In fire safety of offshore platforms. One can also do fire protection by design. You can have fire detection systems, you can also have fire extinguishing systems. Both of them should be provided so that they need to work or operate automatically. They should have or they should be designed with high degree of reliability. Let us ask a question, what are the basic requirements of these equipments? One, they need to be simple in design and easy to operate. Why? Because personnel on board can readily use this. Equipments. These equipments should have, or let us say should not have, high end technologies. to operate. Second, they should be maintained and repaired periodically to check their availability on demand. Thirdly, fire drills should be conducted to train personnel on board to use these equipments. There is a very interesting question asked, what is the basic problem in offshore platforms that makes fire protection very difficult? Offshore platforms generally have congested layout, of topside equipments. They operate in a very confined and compact space. Offshore production equipments are not generally laid horizontally, but laid vertically. So, we need to have fire protection along the height or depth, but not along the layout. There are extensive space and weight limitations of fire protection equipments to be provided on board. Since sea water is very corrosive, if this water is used for fire protection, it can cause very serious consequences to these equipments. Further, it is also harmful to human on board. Therefore, there is a high demand of pure water to be used for fire protection systems. In offshore platforms. Let us ask a question, what are the fundamental or let us say general design requirements of fire protection systems in offshore platforms. One, they should be or they should consume low firefighting agents like water, foam, etc. They should have low firefighting agents consumption. Secondly, they should be compact in size and weight. They should be easy to operate. They should be completely automatic. That is a very important issue. They should be rapid activation systems. Because fire outbreak should be extinguished before it causes serious damage. Offshore platforms are generally aided with offshore platform support vessels, what we call PSVs. So, friends, what would be the general fire protection requirements of such support vessels? We will discuss them in detail in the next lecture. In this lecture, we understood explosion models which are useful to estimate the energy release. We understood some basic issues related to fire protection systems to be used in offshore platforms. We have also understood what are the basic consequences of fire in offshore platforms like fireball, flash fire, blavey, etc. in detail. We will discuss about the fire protection systems on PSVs in the next lecture. Thank you very much.